Let me know if it starts getting squirrely, all right?
Yeah.
Okay. All right. So am I good here if I write notes here?
Yeah.
What about over here?
No. Your finger just makes it.
So I got like this?
Hand like just.
I'm good here?
Oh, yeah.
All right, okay. All right. Single bond, double bond, triple bond. Which one's the strongest? Triple. And it's the shortest. And that the pencil example, right? Super strength Adam showed us, okay? So you break one pencil very easily, right, Adam? You broke two, not so bad. Three, he couldn't break three. He had a leverage issue, but if you have three of those pencils on top, that's the three bonds. It's hard to break. And obviously one pencil is going to be longer than if you cut it in half and then again. So the point is triple bond, the atoms are close together because their attractions are very strong. That's why the triple bond's the strongest. All right, moving on. So we've talked about polar, nonpolar quite a bit. Distribution of charge we talked about. We did that. All right. Last two things with covalent stuff, then we'll do the like dissolves like, and then I'm going to show you something on metallic bonding. Here we go. So dipole moments. Dipole moments. Polar molecules have these. Nonpolar molecules do not. Polar molecules have these, nonpolar molecules do not. I'm actually going to show you something up here. I have this like simulator, it's like animation thing that I can manipulate that shows what the heck these are. I'm going to give you a couple examples first, then I'll show you that. All right. So dipole moment. What the heck does the word dipole mean? Aaliyah, what's di mean? Two. What's pole mean, Hannah? Not like this thing.
Yeah, I know. Like, the furthest part.
Maybe opposite ends?
Yeah.
Yeah. So di means two, pole means kind of like opposite ends, like poles on a battery, or polar molecule, right? North pole, south pole, so kind of opposite, right? So polar molecules have these. And dipole moment depends on difference in electronegativity and symmetry. Two things we've already learned about. So this is the last thing I teach with the polar nonpolar, because you need to understand what polar nonpolar means first before you can understand this. At least I think. Maybe some teachers teach it the other way, but this is just how I do it. All right. So I'm going to give you two polar molecules. I'm going to give you two nonpolar. And you're going to see how the polar have these. Again, you'll see what these are. And how the nonpolar do not. Oh, and before I forget, and for period 7 as well, after we do some notes, I'm going to give you a worksheet. So if we have some time at the end, you guys can start it. The plan is to have a little time for period 7 to start it, since I'm not going to be here. So we'll see. Sometimes all the time I talk too much, so we'll see. All right, questions here? Can I erase? Can we move on here? All right. Okay, so I'm going to give you two polar, two nonpolar, and we'll see how these things have dipoles. So I'm going to go with HCl. That's our polar molecule. We'll go with water, except I'm going to draw the dot structure for water. We have to remember water is polar. And you know what? We could actually show the dot structure here as well. I didn't show the little bond there, but there would be the dot structure for HCl. So there's your two polar. Two nonpolar. I'll pick a diatomic. Someone give me one. Morgan Heath, thanks for volunteering. Just want to make sure you're awake back there. Maybe because you're too cozy with the coat on.
It's really cool.
All right. BR. BR2. BR2. Bang, 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 bang. There we go. There's our dot structure. Very nonpolar. All right, Matt, if I go to the right of this, am I out?
You're good right there.
I'm good right here.
Yeah.
What am I right here?
That's like just like if you
Draw a line.
If you went
I'm just gonna put it here. I'm gonna put it down here.
All right.
All right. So there's BR2. I'm gonna do CCl4. So these are the same ones that we do over and over because there's only so many, polar, nonpolar molecules you're going to see. So go ahead, get all these down. And I'm just going to show you, oh, so these two are both non-polar, I'll just leave that. So I'm going to show you what a dipole is, show you how the polar have it, non-polar do not, then I'll show you that little simulator thing. Actually, I take that back. We're going to take some notes on properties first, then I'll just show you everything at once so I don't have to disconnect it and hook it up twice. All right. So period 7 is going to be watching a video within a video. Crazy, Adam. It's crazy. All right. Dipole. Here we go. Ready? Big build up to what the heck a dipole is. That's a dipole. It's an arrow. It's it with a weird little line there. That line isn't at the end of the arrow. It's just in a little bit. But actually, that's a really nice little feature. I'll explain.
The dipole, Colin.
That's a dipole, Colin. What is a dipole? Read your notes. It depends on difference in electronegativity and symmetry, correct? Yes, that's what I just wrote. Okay, look up here. Look up here. HCl, is it symmetrical? No. H2O, is it symmetrical? No. Because they are not symmetrical, they have what's called a dipole. What the heck is that? It's easy. The arrow points towards the element with the higher electronegativity. That's it. Think of the tug-of-war analogy I use all the time. These two are sharing electrons unequally. Cl is way stronger than hydrogen. Cl 3.2, H 2.2. So that arrow just tells me what direction the electrons are getting pulled in. Same thing here. Oxygen 3.4. Hydrogens are both 2.2. Now, in the past, kids have said, wait a second, 2.2 plus 2.2, that's 4.4. That's stronger than 3.4. Doesn't work that way. It actually treats each bond separately. So oxygen wins this one, and oxygen wins this one. So in general, it's going that way. The oxygen's pulling the electrons that way. The arrow points towards the more electronegative element. That's what a dipole does. Now, over here with these two, I kind of lied in the notes. They do have dipoles sometimes, but guess what? They cancel out because, come on, they're symmetrical. Very good. So here, the BR is pulling and the BR is pulling. It's like playing tug-of-war with yourself. Okay? No one's going to win. So these actually cancel out, so there is no dipole. No dipole and nonpolar. Here, this one's a really good example. If Cl has an electronegativity at 2.6, and carbon 2.6, yeah, I think so, and Cl is 3.2. So all these Cl's are 3.2. So eyes up here. Each bond is a polar bond because there is a difference in electronegativity. But what happens is this Cl is pulling really hard, but so is this one. They're opposite each other, so they cancel each other out. Nobody wins. Same thing here. Cl pulling down, Cl pulling up, nobody wins. So they cancel out. So technically there are little dipoles here, but because they're opposite of each other, nothing really happens. So we say there's no dipole. So that's what dipole moments are. It's an arrow. In real life, what is it? It's where the electrons are kind of grouping together. All right? The electrons are kind of grouping or hanging out over here, and they're hanging out over here because of that difference in electronegativity. Okay, here it's equally distributed. You learned all this already. I'm just applying one more thing to it. It's called dipole. Okay, there's nothing new to learn after this. Now, what does that kind of look like? What? A plus sign. Very good. You've seen me do this before. This side of the molecule is partially positive, so it has that weird little symbol. This side of the molecule is partially negative. Why? All the electrons are being pulled that way. Electrons are negative. So if you were to split this right down the middle, the right side is more negative, the left side is more positive. I want to make something very clear here. These are not negative positive charges like Na plus Cl minus. This is not ionic. It's polar. It's different. They're still sharing electrons, so we're not transferring, but it's slightly negative compared to this side, which is slightly positive. All right. So again, imagine the tug of war with like what do you call it? Like a flag in the middle, okay, or something in the middle of the rope. That flag or whatever, let's say, is an electron. It's going to be pulled this way, so this side will have that flag, so it's slightly negative. It's not like hydrogen's letting go. It's just it's more on this side. Okay, so that's what these charges, these partial charges, are all about. You've seen me draw them before. It's this dipole. Same thing here. Oxygen is partially negative, and the hydrogens are partially positive. You need to label that. Okay. Where I drew the arrow, don't let that confuse you. All right. It's just you could draw the arrow anywhere you want. It's just showing they're going this way. Okay. So oxygen's partially negative. It's probably not a good idea I put it there. Might be confusing some of you. Let me fix that. So I could just put it to the side. Okay. Maybe that helps a little bit. So this is partially negative, and then these are partially positive. Over here, we have no partial charges. Everybody is balanced. We don't have these things. Dipole, two poles. One pole here, one pole here. Negative, positive. Negative, positive. Those are two poles. Dipole. That's where it comes from. Here, we don't have poles. No poles because nobody wins that battle. No one wins the tug of war. That's it for dipole. Okay, there's going to be some questions on that worksheet to ask you. You know, that's going to be asking you about this. So we're moving on. Okay, last thing with this covalent business, and then I'll show you the little symmetry thing I have, polarity thing, and then the metallic. Just want to make sure we're good with that. All right. Oh, and the like dissolves like. I have a video for that as well. All right, so covalent properties. What's another word for covalent? Molecular. Let's put that. Covalent / molecular properties. Okay. How we doing there, Matt? Looking good? It's not like zooming in, zooming out.
You're good.
All right. Okay. What'd you learn in lab? Properties of covalent in lab. Two properties you learned.
It melts. It has a long.
Right. They melt easy. Low melting point. Low melting point. You know what? I'm also going to put parentheses or a little slash here. Boiling point. We didn't see that in lab, but I'm telling you, if they have low melting points, they have low boiling points. Low melting points, low boiling points. And Mike Flower, what does that mean in terms of forces of attraction? Weak. Weak forces of attraction. Covalent compounds are weak compared to ionic. Weak. Ionics are stronger. They have high melting points. What else did we learn about covalent? Put them in water, throw some wires in there with electricity, nothing happens. Do not conduct electricity. Do not conduct electricity, and this is why they have no ions. Underline that. They don't use ions. So there's no charges in there to conduct. They don't conduct as a solid, as a liquid, dissolved in water. I don't need to put any of the specifics, just this is it, period. They don't conduct. Okay. They're soft. Soft solids compared to ionic. Compared to. A lot of properties in chemistry are all relative. What are you comparing it to? They're softer compared to ionics. Why? Because they're weaker. Those are the big three, okay? Those are the big three. All right, so that's probably all I'm really going to get into there. So low melting point, boiling point, they're weak. They do not conduct, and they're usually softer because of that. All right? Okay, so now what I want to show you, we got about 10 minutes. I'm going to show you the video on like dissolves like. I'm going to show you the video with the polar stuff, and then metallic bonding. So don't put your notes away. I need you to take notes on what you're seeing. In your notes, let's just write the phrase like dissolves like. Like dissolves like. Sorry, that's messy there. Like dissolves like, and I'm just going to put down what that means, and then we'll watch some things here. When we go over solutions, that's a unit, solutions, which is coming up soon, we talk about this a lot more. So I'm going to introduce it. We talked about it in lab, but we'll get there again. So what does this mean? Who remembers? What does this mean? What does that phrase mean? Right. Polar will dissolve polar. And nonpolar will dissolve nonpolar. So if you have a stain on your shirt or ink on your shirt, water will not get it out because the stain or the ink is nonpolar. Water is polar. So water alone doesn't really get things clean. You wash your hands. You don't just use water. It doesn't work as well. You use soap and water. Guess what? Soap is nonpolar. So is dirt, stains, ink, whatever it is, also nonpolar. Okay? So you need something that's similar to dissolve the crap off your hands or your clothes. Now, it's a little more complicated. Soap is nonpolar, but there's parts of it that are polar, so when you're done washing, the water will kind of wash it away. So that's a little tricky. But anyways, the concept there, think of oil and water. Okay? Water will not mix with oil. That's because water's polar, oil's nonpolar. Okay, so this is what it means. I'm just going to add one more here. Ionic will dissolve in polar. Now, circle the word will because I'm sort of lying. Not all ionics will dissolve in polar, but a lot of them will. And the reason for that, this like dissolves like, is they have similar forces of attraction. We talked about that in lab with the Na plus Cl minus attracted to those partial charges on water, which we just learned about. So that's really what this means, is they have similar forces, therefore they're attracted to each other, therefore they dissolve. That's what this means, okay? I got a video to kind of show this happening, okay? Salt dissolving water, it's a good video, all right? So first thing I'll do is show you that, then I'm gonna play with that animation thing, it's kind of cool, to show the dipole, and then the video on metallic bonding. So, in our notes after this, you're going to write metallic bonding, and I'm going to have you take notes on the video. So I'll tell you when we get there. Lights, please. Thanks, Nicole. All right. Okay, so this guy talks about some things you don't necessarily need to know right now, so I'm going to just talk over. So the bond energies we are going to talk about, well, maybe tomorrow, but here's what's happened. I'm going to let you watch. Just watch. By the way, these are what? Water. What's this? Salt. NaCl. Na is the gray, Cl is the green. What's the water doing? What's it doing to the salt? Yeah, it's ripping it apart. When you put salt in water, this is what happens. Water gangs up on the Na plus Cl minus and rips it apart. You see how there's blue flashes and red flashes? I don't know if you're paying attention. See how that's red? And they're not showing I didn't get to it in time, but they're showing some blue. So notice, what part of the water is attracted to the Cl minus? The hydrogen, the red. We just learned why. Hydrogen is partially positive, and these Cl's are -1. Opposites attract. What part of the water is attracted to the Na? The oxygen. Oxygen is negative, partially negative, and the Na plus is positive. So opposites attract. So when you put something in water and it dissolves, this is what happens. No matter what it is. This is just an example of salt. Water surrounds the ions, gangs up on them, and rips them apart. So if you didn't notice the flashing here, watch again. When they connect, you see red. So when these water molecules attach, you see red flashes. And then when they rip the Na+, that's blue. what it's trying to show you is every time a water molecule attaches, it's releasing energy. And every time it rips it apart, it's putting energy in. It has to put energy in to rip the Na apart from the Cl. It's hard to kind of teach that in this video, but that's what this video is actually trying to show. Two things, dissolving and differences in energy. And I'm just going to show you this one more part. So if you want to make hydrochloric acid, hydrogen and chlorine gases, and you put them together to make HCl, it's a synthesis reaction, what it's going to show is it needs energy. So when you put energy in, you break things apart. Okay? When Adam snapped that pencil, he had to use energy from his body to break the pencil. Even if it's easy, you're using energy. So anytime you break something in chemistry, break something apart, a bond, let's say, you're putting energy in. Okay? If you want to chop wood, you transfer energy from your body to the axe, from the axe into the wood, and the wood splits. So you're transferring energy into that wood. That's why it splits. Same thing here. You put energy in to split these apart. Then the cool thing with that is, once you rip them apart and then put them back together, it's the opposite. When you put things together, energy is released because it's more stable. So when you form bonds, you release energy. That's kind of a double whammy here in this video. So watch what happens. I believe it's going to be blue when they rip apart and red when they come together. Yeah. So when they come off, when they rip apart, that means blue means energy's going in. So that's positive energy. Energy's going in. Red, negative, releasing energy. And it's just showing that overall, when you make HCl, it actually releases more energy than you need to put into it. So it might be a little confusing, but I was using that to kind of teach two things at once there. All right, so we will talk more about that tomorrow because I'm obviously going to run out of time. All right, so anyways, the main thing of that video right here. How does the water attach to the crystal here and rip it apart? It's the opposite charges. Okay, now the other thing here, we're not done, don't pack it up. This thing is cool. So see that arrow, what is it?
Dipole.
Dipole. Look up here, electronegativity of atom A, electronegativity of atom B. Which one would Adam Esposito be? He's going to be this one. He's winning the battle, right? And you jump ball, you're getting it, Adam. Adam's pulling it towards him, okay? So look how this arrow gets bigger the more electronegative that atom is. Watch what happens when I drop it down. This is a very polar molecule, okay? And hold on, I can show you partial charges. There we go. There's those things, okay? Now, watch what happens if I drop the electronegativity of B to 0, just like A. No dipole. No dipole. So if they both have low electronegativity, nobody wins the pull. What happens if they're both strong? Same thing. If these two are identical, there's no dipole. We call that nonpolar. Okay? Look at the electron density. Yeah. Watch what happens. Darker meaning more electrons. We could do it a different way, electrostatic potential. This is that positive negative attraction. Red means lots of negative electrons. Blue means not a lot. So the stronger that dipole, the bigger the difference in electronegativity, the more polar that is. And watch what happens if I drop this to 0. There's no difference at all. That's nonpolar. Okay? That's nonpolar. So I wanted to just show you that one example. You can actually use real molecules and do the same thing. So there's HF. All right, there's your dipole, your bond dipole, right? If we use F2, watch what happens, nothing. There's no dipole, nothing, because it's nonpolar, right? So I could go on and on with that, but that's just another visual for that. Last thing here, I wanted to start this today. You know what? You could actually pack it up and just watch. I'd prefer you to just watch instead of worry about writing things down. So I'm going to show you this. We'll take notes on metallic bonding tomorrow. So just watch this, and then I'll hand out the worksheet. So the worksheet is due tomorrow as homework here. This might be super loud, we'll find out.
Metals are used in many everyday objects. This morning, when I woke up, I decided to have a soft-boiled egg and a cup of coffee. The pot I used is made of metal. The kettle is made of plastic.
Try to just ignore her voice. I don't know why I think it's so weird, but moving on.
But the coiled heating element inside it is made of metal. Metals are good conductors of heat. This is the reason why metals are used to make these everyday objects. You would never see a pot made of wood or a heating element made of plastic. Metals are also good conductors of electricity. The wire connecting your kettle to the electrical socket is actually made of many copper wires, insulated with a layer of rubber. Think about the shapes of the everyday objects we described. The pot, the heating element inside the kettle, and the copper wires. Notice that they are very different. Metals are malleable. This means that they can be molded into different shapes. Metals are very ductile. This means that they can be stretched into wires. To fully understand these properties of metals, we must understand metallic bonding. When we talk about metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the free-floating electrons around them.
So that's what metallic bonding is. It's called a sea of electrons. Okay, I'm going to stop it there because the bell's going to ring. That worksheet, front and back, due tomorrow. Okay, so that's it. Bell's going to ring real soon here. Are you